Marta. I'm very excited about this One Non-Local World initiative and this opening event, and it's a great privilege to be able to present this talk today. My talk is on the role of non-locality in continuum mechanics, and I've been developing the paradigmatic theory for over 2 decades. And during that time, I've made some observations about the origin and uses of non-locality in mechanics. And that is what I'd like to tell you about today. I will start by discussing what non-locality is and where does it come from. I will present a simple demonstration showing that a non-local continuum model emerges from a smaller scale model of a heterogeneous material. Most of my talk will be about how non-locality is useful and how it can open new doors and give new insights into practical problems of real interest in the engineering world. What is non-locality? There isn't a unique definition of non-locality, but what I mean is non-locality is a property of a mathematical model that introduces a length scale or possibly a time scale into the solutions other than the scale that is dictated by the geometry of the problem or of heterogeneities in the material or the scale of the applied loading. So for example, in these figures on the left, this is the stretching of a membrane under a concentrated load applied at the center. A local model would give this sort of stretched rubber band solution, whereas a non-local model, such as a beam theory, would introduce its own length scale, L, that shows up as this curvature in the figure. So the standard theory of continuum mechanics, in one dimension, the equilibrium equation is shown here. That is a local model. If we add additional derivatives of U, as would happen in a strain gradient theory or beam theory, these parameters that show up in the equation can be have dimensions of length, this additional parameter L. So that is what determines the length scale in the solutions. So those are that's an example of a weakly non-local model, meaning that the parameters in a PDE can be reorganized into something that has dimensions of length that influences the solution. In a strongly non-local model, the length scale shows up explicitly through the integration of some interaction over finite distances. Paradigmatics has a cutoff distance for these interactions called the horizon delta. Where does non-locality come from? Well, the easiest case to understand is when there are physical forces that are really and truly non-local, that is acting across a finite distance. So the classic example of that is electrostatic forces, which clearly act over finite distances. At smaller length scales, van der Waals forces and surface forces are other examples of physical phenomena that are really non-local. At still smaller length scales, interatomic potentials that are used in molecular dynamics are explicitly non-local because they describe interactions between particles across a finite distance. So that is the easiest case to understand. What's a little more subtle and is a little harder to sell to engineers who are considering using non-local mechanics is when there aren't really and truly physically non-local forces involved. Yet um, non-local mathematical models still can have a lot to offer in generating solutions to problems of practical interest. So I'm going to uh, show you how a strongly non-local model emerges from a simple approach to smoothing or homogenization of a smaller scale system. And what I'll be talking about is the coarse graining of molecular dynamics. And rather than take the usual approach of trying to define a stress tensor that's appropriate for molecular dynamics, I'm going to start by defining kinematical quantities that are appropriate for a homogenized non-local model. So in continuum mechanics, the exact positions of uh, uh, atoms and molecules is not a very much use. Instead, we always deal with smooth quantities. So we'll consider a molecular dynamic system where each, uh, where the particles interact through some potential, which could be a multi-body potential. And they obey Newton's second law individually. And the forces are whatever is derived from this interatomic potential. To convert this to a continuum description, we'll define smoothing functions omega. And in this notation, x is the center of the smoothing function, and p is the atomic position in reference configuration. So these smoothing functions in general overlap with each other. And the center position, that is x, the smoothed displacement at each x will be our homogenized degrees of freedom in the continuum model. We defined the smoothed quantities as shown in these expressions, continuous mass density, which is just the weighted average of the masses of the atomic masses within the radius of the smoothing function, smoothed applied loads, and this mass weighted displacement field. So the next step is to investigate what is the evolution equation for these homogenized degrees of freedom. To derive that, we first take the second derivative of this homogenized displacement with respect to time, giving us this equation. The individual atomic positions, as I mentioned, are described by Newton's second law. And when we do a little more algebra and evaluate what's on the right-hand side of this equation, we end up with this expression. So what appears here is the integral of what are called bond forces, which are defined here. And those are basically made up of the weighted averages of the force interactions between the atoms. So the striking thing about this expression is that it's a non-local uh, continuum mechanics law for the linear momentum balance. And this is the paradynamic equation of motion. So what we've done so far is derived a non-local continuum model from what seems to me to be the simplest concept of smoothing of displacements. And the non-locality arises from two places. First of all, the non-local interactions between atoms, and also the overlapping of the smoothing functions, omega. The size of the radius of these smoothing functions determines the cutoff distance, that is the horizon in the paradynamic law. What's missing from this is a material model that's appropriate for the non-local momentum balance. So that doesn't come out immediately from the analysis I just described. However, you can use molecular dynamics or other small scale model to help derive a non-local material model that's suitable for paradynamics. For example, this is a molecular dynamics model of a graphene sheet, which is being stretched at a constant rate isotropically. So here on the left is the molecular dynamics model, and on the right, it shows the smoothed displacements derived by the method I just described. This method also provides the forces between the smoothed degrees of freedom, and those can be fitted according to a non-local material model based on the molecular dynamics results. So that is a simple demonstration of where non-locality comes from. And next, I'd like to turn to how non-locality is useful. Well, one way it's useful is in regularizing solutions to the local equations. What I mean by that is the local PDEs can evolve into solutions that end up being inconsistent with the PDEs themselves. So I'll talk a little later about fracture, but an even simpler example is shock waves. If you hit a cylinder full of air with a solid piston, the wave pattern that emerges is we start with a gradual increase in pressure behind this propagating wave, but the wave becomes narrower and narrower as it propagates. And according to the local theory, it ends up becoming a discontinuity in stress, which is called a shock wave. The problem is that this discontinuity is a singularity that the PDE of the local theory can't be applied to. So a finite element or finite difference code would get into trouble if applied without modification at this singularity. And the way everybody works around that problem is by introducing a term in the local linear momentum balance called artificial viscosity. And what that does is it adds a compressive stress that depends on the strain rate at any point. This was discovered by von Neumann in 1950. How about that? So that's 71 years of artificial viscosity, and everyone still uses the exact same idea because it works very well. But my point is this is a type of non-locality that is introduced to regularize the local model, and its effect is to spread out the shock wave over approximately 6 elements, and after that, everything works just fine. Paradynamics is designed to model fracture as well as other things. So that's an even stronger singularity than the shock wave I was just talking about. And paradynamics regularizes fracture due to non-locality, non-local interactions combined with a simple model of bond damage, which is called bond breakage. And that simply means that as a bond is extended beyond some critical strain, it breaks irreversibly, and after that, it no longer sustains any interaction force. So what's shown here is the strain right in front of a crack tip. And the dashed line shows the famous 1/r singularity of linear elastic fracture mechanics, which everyone agrees is non-physical. The other lines show paradynamic solutions asymptotically approaching the crack tip, which don't blow up, they are bounded because of non-locality. But as the length scale, that is the horizon, becomes smaller and smaller, these asymptotic paradynamic solutions do approach the linear elastic singularity. The main feature of paradynamics that people like to work with is unguided crack growth, meaning that using this autonomous model of bond breakage, that is, the bonds break whenever they want to according to the local loading conditions, we get propagating surfaces of damage that organize themselves into two-dimensional, possibly curved surfaces that we interpret as cracks. But the point is, nobody's telling these cracks what to do, how fast to grow, when to nucleate, when to stop, when to branch, and so on. Everything happens spontaneously. This is a video showing how this non-local model can be used to investigate how a distribution of initial defects organizes itself, and due to the interactions between these defects and their spontaneous growth, how these organize themselves to propagate a macroscopic crack in a brittle material. This shows that a non-local approach is a natural way of modeling fragmentation for the same reason. You can imagine how difficult it would be to model something like this with XFEM or other special techniques that have been developed in the finite element community. So that's regularization. Another use of non-locality in practical simulations is in creating surface energy. In material science, many phenomena are dictated by surface energy and the tendency of material systems to reduce that surface energy over time. So what that has to do with non-locality is shown here. If we have a non-local continuum model in which the bond energies follow this sort of Leonard Jones looking shape, the bottom of this potential well is the most stable. So the system likes to have as many bonds as possible at the bottom of this curve. Now, in the interior of a body, this center point has all its bonds sitting at the bottom of this curve, so it's happy. But if there is a free surface present, then some of these bonds are missing. Therefore, they do not contribute to the total energy of this point. Therefore, this point near the free surface has higher energy, creating surface energy. So that simple principle can be used to model phenomena like this, driven by surface tension in fluids. This is the dynamics of two water droplets that collide, and the resulting oscillations. This is a similar situation representing grain growth and coalescence in a solid. The idea is we have a bond force function of strain that has this up, down, up, non-monotonic shape. The downward sloping part is unstable. So bonds want to be entirely in one stable branch or the other. That's not possible um, because of the boundary conditions. So the way this problem evolves is we start out in the unstable part, and at time zero, we get this burst of grain boundaries, all of which has a finite positive energy associated with it per unit surface area of the grain boundary. So the system evolves to reduce that total surface area. Therefore, the grains try to grow and coalesce with each other. Another use of non-locality is in wave dispersion, which is a manifestation of smaller scale material heterogeneities, that is smaller scale than the cutoff distance delta. In real materials, if you try to propagate a stress wave through a heterogeneous microstructure like this, the wave front is not a plane anymore. It distorts and it gets bent out of shape and it gets slowed down. So that results in wave dispersion, which is the dependence of wave velocity on frequency or wavelength. In real material, long wavelengths usually have a velocity that is given pretty closely by the effective elastic modulus in the local theory. But at shorter wavelengths, this tortuosity of the path of the wave travel becomes important, and the wave velocity slows down and eventually sometimes reaches zero, resulting in a band gap type phenomenon. A non-local model can be used to incorporate this behavior in a homogeneous material model. For example, this is an impactor hitting this composite, and each of these stripes has a different elastic modulus, resulting in a different wave speed. So in a detailed two-dimensional calculation, we see all sorts of complex behavior. So it may seem like kind of a hopeless task to try to come up with a homogenized model that represents this. If we define the homogenized degree of freedom as being the average displacement along a vertical cross-section, then we can tune a paradigmatic kernel or micromodulus function to match the observed spreading of this wavefront and many features of the oscillatory behavior behind the wavefront. So that's an example of how non-locality can be used to incorporate multi-scale effects in a homogenized model. Another use of non-locality is that it opens new doors into the general phenomenon of material stability. An example of that is this calculation of the stretching of an elastic bar, which has this non-monotonic shape in its bond force material model. The downward sloping part is unstable. So as the bar stretches, it can't just, so we're traveling up this stable branch, and then we go over the top of this peak into the unstable part. And it can't stay there forever because it has a negative dispersion relation there, and small perturbations grow unboundedly over time. But what distinguishes the non-local model from the local model in problems like this is that the instabilities grow at a finite rate, meaning that we can do actual mechanics in this unstable region, leading to a finite rate of growth of defects into macroscopic material failure. In contrast, in the local theory, the whole solution would blow up as soon as it reaches the top of this stress strain curve, because in the local theory, instabilities happen instantaneously rather than at a finite rate, as I just described. Material modeling in non-local methods also opens new doors into mathematically describing material behavior. And one way to look at that is to note that in local theory, material modeling is six-dimensional because there are six independent components of stress and strain. Whereas in a non-local theory like paradynamics, material modeling is infinite dimensional because there are an infinite number of bonds, each of whose forces can be prescribed independently according to the deformation within the horizon of a material point. So this has led to the development of all sorts of interesting material models in paradynamics that describe all kinds of useful phenomena like plates and shells, dispersion, which I already talked about, composites, and various failure modes within composites, and even solitary waves, which are similar to solitons. The complexity of material modeling in a non-local setting is a legitimate application of machine learning, and many people have made this observation, and currently there's a lot of activity, such as the paper shown here, aimed at learning non-local material models from experimental data or from smaller scale simulations. An interesting feature of non-local modeling is that in the limit of zero interaction distance, the non-local theories approach the local theory, and that can be proved rigorously. But the converse is not true, meaning that the local theory does not somehow imply a non-local theory. But I believe that it's possible to learn a lot about the properties of the local theory by looking carefully at this process of convergence. For example, in the grain boundaries that I talked about a little while ago, what happens to the energy that's stored in these grain boundaries as the length scale approaches zero? Why is it that the non-local theory continues to have finite energy at these grain boundaries, but the converged limit is the local theory does not? So I think that's the kind of fundamental question that is sort of crying out for someone to take a look at. We have in the non-local community our very own peer-reviewed journal, which is called the Journal of Paradynamics and Non-Local Modeling. Some of the staff are shown on the left here. Many of whom are in attendance at this online conference. The scope of the journal is all things non-local, covering the spectrum from basic math and numerical methods to material modeling and applications. So our hope is that over the long term, this journal will become the first choice for people publishing papers in the non-local community. In summary, I've described where non-locality comes from And I've talked about how non-local methods are useful and how they can provide new opportunities and challenges to people working in continuum mechanics. So thank you for listening. I'll stop there.